Okay, so I have to apologize for missing today's lecture. I completely lost track of time. I've never done that before, so sorry about that. But anyway, I did want to talk about something I think is uh, um, pretty much needed for doing your project. Two things. So we're going to talk about stringer buckling and then the top plate buckling. So I'll split these up into a couple videos. Um, So first, let's talk about the buckling of the stringers and how that is related to the rib spacing. Okay, so basically, one of the functions of the ribs, as well as to keep the bending of the beam beam-like, is also to prevent buckling of the stringers and, to a lesser degree, buckling of the top plate. So what I've drawn down here is a cross view. If you want to think of this as a wing, we are looking down the wing span, and those vertical elements are the ribs. Okay, and then on the top we have stringers, and we have a bending moment due to the lift that's applied onto that section. We'll discuss that. And that may or may not cause the buckling of those stringers. Okay. And in this case, A is going to be the rib spacing. All right. So if we look at the buckling of a column, and we're going to treat the stringer as a column, this is the Euler buckling equation, right? It's pi squared times EI over the length of the column squared, okay? So in this particular case, obviously E is going to be Young's modulus of the stringer, right? Now I, this is the one that kind of gets a little bit, sometimes it'll get a little confusing because we're going to bounce back and forth between properties for the stringer, properties for the total cross section. So in this case, I is going to be I of the stringer. This is I. Okay. So maybe we have a stringer that is a hat section. So it would be the I of that stringer about its neutral axis, right? It would be that. And L in this case, if we look at this, this is going to be the rib spacing A. Okay. And if we look at this as well, the way these modes tend to go, the end condition of pinned at both ends is not a bad assumption. So in that case, really this is the effective length. And so the effective length is actually equal to length itself. And so that is the rib spacing. Okay. All right. So the idea here is we can calculate the critical buckling load knowing the stringer, right? So really we need to just know the I of the stringer itself and what goes on there. So for this particular setup, the critical buckling load for the stringer is going to be pi squared E I of the stringer, right, over A squared, where A is the rib spacing. All right. So that's basically all you have to do there. Now, one of the questions is, okay, what is the actual, I should say it this way. Okay, so once you know what the buckling force is, then the question is, what is the actual load seen in that stringer that would cause it to buckle? Okay. And if you remember, to do this, right, we look at, again, back to conventional beam theory. And if this is, the stringer, right, we are going to integrate the stress over that area, right, where the stress is going to be bending moment times y over I. Now, in this case, this I is the I of the whole cross section. Not the I of just the stringer, right? So that's going to be your box section with whatever stringers you have here. It's going to be the I of the entire section about its neutral axis, not the I of the stringer, right? Because we're talking about the global bending of the whole box. Okay, and so in this case, P is going to be the integral over the area of the stringer, the cross-sectional area of the stringer, of the stress, dA. That's going to give you a force, and that will give you M over I times Y dA, and this quantity here becomes Q. All right? Okay. So actually, the P applied is going to equal, let me explain this in a second. I didn't do this exactly. I probably should have explained it a little bit differently to start with, but that's fine. Okay, so in this case, this is the force in this. This is going to be the compressive force in the stringer. Okay, delta M is going to be the change in M across the rib spacing. All right. It's the change in M from here. I should just call this M. And here is M plus delta M. Okay. So it's the change in the bending moment over that section. All right. And Q, this looks like an A. This is supposed to be a delta. Sorry about that. Q is the Q of the stringer itself. So here, let's say we have a stringer again, and now here is the neutral axis of the box section, or the wing, whatever you want to call it. And so we are going to get the Q here, right? Where this is Y bar and this is A bar. And Q is going to equal A bar times Y bar. Okay? And so that will allow us to calculate the compressive force in the stringer and compare it to the critical buckling load. Okay? All right. I'm going to stop there, and then I will do an example.